Hello everyone. I hope all of you are doing well and staying well. So today we're going to be looking at rigid body kinematics, and we're going to perform a general velocity analysis. Okay, so this is also sometimes called as the three-term velocity equation. Okay, so to start off this proceedings, and we're going to be extending this idea to performing acceleration analysis as well. Okay, it'll be the same thing. So to start off, I'm going to just draw a rigid body. Okay, in the following sense. So I have a rigid body which is sitting there. This is at some point in time t. Okay, and let me say that the rigid body, I'm interested in a point on this rigid body which I'm going to mark as the point A. Okay, and let's say that there is another point B which is outside the rigid body. Okay, so there is a point B. Okay, so this is a point B which is outside the rigid body. So point B is outside the rigid body. Point A is inside the rigid body, or within the rigid body. Okay, and so this essentially means that B can be a part of another rigid body. So which essentially means that the point B could be a part of another rigid body. Okay, so for example, if I drew something of that kind, okay, and maybe if I do this in like dotted lines or something of that kind. So B could be a part of another rigid body. I'm interested in the motion of this body A. Okay, this body A, let me say at this point in time, has a certain angular velocity and an angular acceleration. Okay, so this is the angular velocity omega of the body, and then I'm going to say that it has an angular acceleration as well, and I'm going to just assume these directions. Okay, let us just say this is the situation. Okay, so let me just call this as A, then this is B, okay, then this is C. So omega and alpha are angular velocity and angular acceleration of the rigid body of interest. Okay, so this is a rigid body. The one that is drawn in the dark color is the rigid body that I'm interested in. Point B is a point on another rigid body. And here is the idea. I want to look at the motion of point A and point B from the perspective of an inertial observer. Okay, so I'm going to set up an inertial observer who is sitting right outside the frame of the problem. Okay, so here is the X, Y, and the Z direction which is coming out of the page. So I'm going to draw that as well. Okay, so here is the I direction, the J direction, and the K direction, and here is the inertial observer who I'm going to call as O. Okay, so this is point O is an inertial observer. Okay, one thing I want to make a note of is I want to define what is called as a triad of unit vectors. Okay, triad of unit vectors, or a unit vector triad. Okay, so in a sense, a triad of unit vectors contains three mutually orthogonal unit vectors. Okay, and so for example, ijk is a triad. Okay, so for example, ijk is a triad. Okay, and the general rules of the triad is that if I take the dot product of I with j, this is 0, and if I take the dot product of j with k, this is 0, and k with I, this is 0, right? And then if I also do the following, I cross j is equal to k, then k cross j is equal to I, and then this is j cross k, I'm sorry, so I got to change this guy here. So this is j cross k, and then k cross I is equal to j. Okay, so this is the last one. which has to be true in the triad. So this is k cross I is equal to j. Okay, and a very nice way of remembering this is by the following figure. Okay, so to remember this, okay, so you draw this figure I, j, and then k. Okay, and then you go in the clockwise direction, and then you put a positive sign there. So this tells me that, okay, if I go from I to j, I cross j gives me k, j cross k gives me I, k cross I gives me j. Okay, so this is the same thing. Okay, so this is the best way to remember a triad. So whenever you're going to see a triad, I'm going to be drawing these kinds of figures from now on. So first of all, I have a triad I, j, and k. Here is further what I'm going to be doing. Okay, so the triad has been defined. Any three mutually orthogonal unit vectors will be a triad. Okay, and typically if you are performing general planar motion, one of the unit vectors is going to be into or out of the page. In this case, the vector k is out of the page. Now I'm going to take this body A, and then I'm going to take a pair of three mutually perpendicular directions and just stick it onto this body. Okay, so let me draw it in this different color here. Okay, so I'm going to say that this is some direction here, this is another direction here. Okay, and then this is a direction that is coming out of the page. Okay, so I just want to make sure that this is indeed not the same as that. Okay, so I'm going to call this as system E1, E2, and then E3. Okay, so E1, E2, E3 are a set of mutually perpendicular unit vectors which are attached to the rigid body. Okay, so I'm going to write that down here. Okay, so E1, E2, and E3 are a set of unit vectors, or a triad of mutually perpendicular unit vectors that are stuck to the rigid body. Okay, which means that the angular velocity of this unit vector, so this is a triad of unit vectors, or a frame of unit vector, or the unit vector frame. So E1, E2, E3 is a triad, which implies that I can write this as E1, E2, E3. I draw my nice circular arrows, and then I get the following. So E1 cross E2 is equal to E3, E2 cross E3 is equal to E1, E3 cross E1 is equal to E2. Okay, and then you also know that, okay, E1 dot E2 is equal to 0, and then so on. And then E1 dotted with E2 is equal to 0, E2 dotted with E3 is equal to 0, E3 dotted with E1 is also equal to 0. Okay, so this is also something that we know. Okay, so this is a triad. This is stuck to the rigid body. So the important thing is this: the angular velocity of the body is going to be the same as the angular velocity of the triad. Okay, so since E1, E2, E3 is stuck to rigid body, the angular velocity of the triad E1, E2, E3 is the same as the angular velocity of the rigid body. Okay, I hope this is making sense. Okay, and So I'm going to go back to my figure. So first of all, I have the triad ijk, which is a common triad, right? And this is I cross j is equal to k, j cross k is equal to I, k cross I is equal to j. And to remember this, we drew this particular figure right here. So likewise, I'm going to say, okay, I'm sticking this triad E1, E2, E3 onto the rigid body, and these are the three unit vectors of the triad. Okay, they are mutually perpendicular to each other. They follow along this particular principle here. Okay, and likewise the same thing held true for ijk as well. Okay, E1, E2, E3 is stuck to the rigid body, so it's going to have it's going to be rotating along with the rigid body, which means the angular velocity of this triad is going to be the same as the angular velocity of the rigid body. Okay, so imagine a potato, stick 3 sticks into a potato, and then try to rotate the potato. The sticks will also be rotating along with the potato. That's essentially what we are doing here. Okay, I'm going to go back to my figure, and I'm going to draw some position vectors. Okay, so my position vector from point O, I'm going to draw one to point A. That did not come out straight, but my hope is it will. Yeah, it did. All right, I'm going to draw a position vector from point O to point B, and then I'm going to draw one more from point B to point A. Okay, so this has to go there, and then arrows. So 1, 2, and then 3. Okay, so this is going to be R, B slash O. That is the position vector of B as seen by O. This is going to be the position vector of A as seen by O. And this is going to be the position vector of B as seen by A. Okay, so look at the direction of the arrow. I'm sitting at the point A, which means I'm a non-inertial observer, and then trying to find the position of the point B. Okay, so that's something that I'm trying to do here. And from basic vector addition, rules of vector addition, you can see that R B slash O is equal to R A slash O plus R B slash A. Okay, or typically we say that, okay, if I have an inertial observer, I'm going to drop the subscript O, right? This is what we've been saying for some time. And so I'm going to say that this is RB is equal to RA plus RB slash A. Okay, so this is something that you see from the basic laws of vector addition. Okay. One more thing I want to do is the following. I want to take this figure, I want to come down here with all of these guys, and I'm going to do a few more things. Okay, so I'm going to copy that, and I'm going to bring that here. Okay, and I'm going to exclusively look at this position vector RB slash A. Okay, so look at this. So let me grab all of I guess I wanted to take this, and let me grab all of these guys. Okay, so let me grab that and let me paste that here. So here is what I can do, right? I can take these directions and I can, I can go all the way up to there. Okay, and then likewise I can take this and then I can extend this. Before I do that, let me get this guy here. Okay, I'm not sure what that was. That looked pretty scary to me. Okay, and so this is the E1 direction. The E2 direction here is RB slash A, right? I can take RB slash A and drop perpendiculars onto the E1 and E2 directions, and I can find the components of this guy, okay, along the E1 and the E2 direction, and that's exactly what I'm going to be doing here. Okay, so here are the components, okay, of RB slash A at that instant in time. This is at some instant in time. Okay, so this is at some time t. So all of this is at some time t. Okay, so I have a component, and I can mark that component in a second. Okay, so this component, let me do one thing. Let me take this E1, I guess. Let me take this guy and then bring that guy down here, and let me do likewise and bring the E2 down here, and then you can see that, okay, I'm going to call this component as R1 of t, and I'm going to call that component as R2 of t. Okay, and why am I saying it is t? Okay, so here is the point A, and then here is the point B. So this is the point A, here is the point B. Why are they functions of time t? Because the particle B and the point B and point A are probably moving away from each other or towards each other or whatever it is happening as time is changing. Okay, so that is why I'm calling them as functions of time. Let me scoot that down here, which essentially tells me that this vector rb slash a can be written as r1 of t e1 r2 of t e2. Okay, and so I just want to make maybe a small divider here, just to say that okay, this is slightly different. I guess it still has a lot of ramifications for our problem, but I just want to make sure that okay, this is the main picture that I'm looking at, and then this is just taking that position vector and breaking it into its components. Okay, so that's essentially what I'm doing on here. Okay, and so one thing I want to mention here is that the points A and B, so everything is changing with time. That almost sounds like an aphorism, right? Everything changes with time. Pretty obvious, isn't it? Okay, so since everything changes with time, I can say that r b slash a is actually a function of time. Okay, so which is why r1 and r2 change with time. Okay, and so we have everything down there. So I'm going to go back to my expression here. So rb, so this is rb is ra plus rb slash a. rb slash a is the position of b as seen from a, and instead of rb slash a, I'm going to substitute for rb slash a from above. Okay, so this tells me that rb is equal to ra plus rb slash a, which is r1 of t e1 r2 of t e2. Okay, you obviously know my next step. I'm going to differentiate it. Differentiate with time, which means that drb by dt is dra by dt plus d by dt of r1 and r2. Okay, and maybe just to have everything down here, so rb slash a is the position of b as seen from a, and then rb and ra is the absolute position of b and a as seen by an inertial observer. Okay, so that's something that you also want to make a note of. Okay, so that's something, and that's something here. And so if I do the differentiation, I get the velocity, obviously, right? So this is drb by dt is nothing but velocity of b as seen by an inertial observer. This is velocity of a as seen by an inertial observer, d by dt of r1 of t e1 r2 of t e2, where I'm going to use the product rule very quickly. Okay, so here vb and va are the absolute velocity of b and a as seen by an inertial observer. Okay, now I'm going to make use of the product rule, and then I'm going to get the following. So vb is equal to va plus dr1 by dt e1 and then dr2 by dt e2. Then I'm going to have r1 de1 by dt r2 de2 by dt. Okay, essentially just made use of the chain rule. R1 dr1 by dt dr2 by dt, I'm just going to write this as r dot. Okay, so this essentially tells me, okay, this is vb is equal to va plus r1 dot e1 r2 dot e2 plus I'm going to have this r1 de1 by dt r2 dE2 by dt. What am I going to do with this dE1 by dt and dE2 by dt is the next question to be answered. Okay, so to think of that, I'm going to take this rigid body that I have. So how do I do dE1 by dt? Exactly the same way that we did things in the normal tangential system or the polar coordinate frame. Okay, so take a look at this. I'm going to take this rigid body. Okay, I'm going to clean it up a little bit. Okay, so copy this, and then I'm going to bring it down here. Okay, so I'm going to get rid of all of that, probably that, then cut that off, and then cut this off as well. Okay, so here is the rigid body at some time t. Okay, let me move this up a little bit. Okay, so this is at some time t. Then I take the same rigid body and then I see, okay, after a time t plus dt, the rigid body is performing general planar motion. Okay, so I'm going to take this rigid body and see, okay, what happens at time t plus dt. Okay, I'm going to copy this and I'm going to paste this, and probably this should have performed some kind of a general planar motion. It's not letting me rotate. Okay, so that's what typically should have happened. Okay, so this is the situation that would have happened, and obviously I don't want this to be causing you a headache here. Okay, plus dt. So this is a time t plus dt, and as you can see that in this time t and time t plus dt, these lines on this rigid body E1 and E2 are essentially lines on the rigid body, right? They would have rotated by an amount d theta. Okay, so during this time interval from t to dt, there is general planar motion taking place. Okay, so which means that if I take these E1, E2 and then E1 and E2 from here, and then if I pin them together, you will see the following is taking place. And just to differentiate between time t1 and time t plus dt, I'm just going to call this as E1 prime and then E2 prime. Okay, so if I pin these two together by their tails, here is what I'll end up getting. Okay, so here would have been E1 and then E2. And I'm assuming that the entire body is rotating about the E3 direction. Okay, so that's something that I can also see very obviously from here. So I'm assuming that let's say something of that nature here. So let us say the body rotates about the E3 direction, which means that omega is going to be omega E3 and alpha is equal to alpha E3, and that's something that I will also write at the beginning of the problem. Okay, so that or the beginning of our derivation, so that we have it in multiple places. Okay, so that's something that I will specify right down here. So let me assume that the body rotates about the E3 direction. Okay, and so let me come back to my figure right down here. So this is E1 and then E2. And then if I take E1 prime and E2 prime and if I pin them together, I get the following here. So this is going to be E1 prime. Okay. And then here is going to be E2 prime. And I told you when we looked at normal tangential coordinate frames that the derivations that we did there would be useful for other things. And this is exactly where it is going to be used for. This is E2 prime. Okay, which means that if I join these two together, this is going to be dE1, this is going to be dE2, and this angle here is going to be an angle d theta. This angle here is also an angle d theta. An important thing to understand is that magnitude of E1 is the same as the magnitude of E1 prime, is the same as the magnitude of E2, is the same as the magnitude of E2 prime, is equal to 1. Okay, these are all unit vectors. Okay, and then it can also be very easily seen that, okay, if I look at dE1 by dt, look at the direction of dE1. dE1 we can prove, as we have done in a normal tangential coordinate frame. I'm not going to do that here. We can prove that this is in the direction of E2. Okay, so maybe let me write that down first. Okay, so we can prove, so similar to what we did for normal tangential coordinate frames, we can prove that dE1 is along E2, or dE1 is perpendicular to E1, and then dE2 is along negative E1, or dE2 is perpendicular to E2. Okay, and then likewise dE1 by dt is going to be the magnitude of dE1 by dt times the direction. So this is going to be along the E2 direction. Magnitude of dE1, if I look at the triangle here, okay, so if I look at that particular triangle there, that's going to be d theta times the magnitude of any one of the unit vectors. Okay, so magnitude of dE1 is d theta times E1 is the same as d theta times E1 prime, which is essentially d theta. Okay, so this is going to give me dE1 by dt is d theta by dt E2, but d theta by dt is nothing but omega. Okay, but d theta by dt is omega, which means dE1 by dt is omega E2. Likewise, dE2 by dt, which is the magnitude of dE2 by dt times minus E1, will also end up giving me dE2 by dt is equal to minus omega E1. Now comes a very important thing. Okay, I'm going to go back and bring my triad. Okay, so look at this. I'm going to go back and bring my triad with all these relationships. I'm going to copy that. Okay, and then I'm going to bring that down here. Okay, now here I can see that, okay, E2 is going to be E3 cross E1. Okay, so which means if I look at dE1 by dt, this is omega times E2, which is omega times E3 cross E1, or this is omega E3 cross E1, right? Just making use of the scalar multiplication of a cross product. Okay, so omega E3 is nothing but the omega vector, but omega E3 is nothing but the omega vector, which means that dE1 by dt is omega cross E1, the omega vector itself crossed with E1. This is a foundational idea. And if I do the same thing for dE2 by dt, okay, dE2 by dt is minus omega E1, right? So this is going to be minus omega times what is E1. You look at E1, okay, so that's that guy here. So E1 is going to be, and then E2 is that guy there, which we had already used. Okay, so E1, if I write it here, is going to be E2 cross E3, which implies that minus E1 is going to be E3 cross E2, right? A cross B is the same as minus B cross A. So which means that this is going to be E1, which is E2 cross E3, or this is going to be omega times E3 cross E2, which tells me what? The dE2 by dt is also of the same form as the previous one. Okay, so this is a fantastic thing, and this is one of the foundational principles in rigid body kinematics. Okay, so summary of the things that we've done so far. So in summary, for any triad, let's say E1, E2, E3, rotating at an angular rate, of omega, we have dE1 by dt is omega cross E1. dE2 by dt is omega cross E2. dE3 by dt is omega cross E3. Okay, this is the foundational principle of rigid body kinematics, where I see the rate of change of the unit vectors. Okay, so this is very, very important. Okay, and for us, dE3 by dt is omega cross E3, which is not very useful for us, right? Because omega is in the same direction, so this is going to be omega E3 cross E3, which is equal to 0, just for us, okay, for 2D motion. But if I have 3-dimensional motion, I have to probably make use of all the 3 of these members of the triad. Okay, so in summary, I have, okay, so for us, so we have dE1 by dt is omega cross E1, dE2 by dt is omega cross E2. I'm going to go and bring my velocity differentiation expressions from before and then wrap this up. Okay, so go back and then bring this big guy from here. Okay, so I'm going to copy that and I'm going to bring that down here. Okay, so we have this, which means if I do the substitution, this is VA plus R1 dot E1 R2 dot E2. Okay, plus R1 times dE1 by dt is now omega cross E1, R2 times omega cross E2. So this is VA plus R1 dot E1, R2 dot E2. Look at this, omega cross R1 E1, omega cross R2 E2. A cross B plus A cross C is A cross B plus C. So this is VA plus R1 dot E1, R2 dot E2 plus omega cross R1 E1, R2 E2. But what do you know? R1 E1, R2 E2 is nothing but R B slash A. Okay, so which tells me that VB is equal to VA. Now watch this. I'm going to write a new expression, VB slash A relative plus omega cross R B slash A. Okay, where VBA relative is going to be R1 dot E1, R2 dot E2. What is the meaning of this term? Okay, here is the meaning. VB slash A relative tells me, okay, hey, if I fix the rotation of A, if I don't rotate the body A, but I just let the points A and B move relative to each other, here is the relative velocity. Okay, so this tells me that, okay, if I fix the rotation of the body and just look at A and B moving as two particles, VBA relative is the relative velocity between A and B. With A on a non-rotating body. Okay, that's one thing. Then what is omega cross RB slash A called? This is the idea. If I'm looking at omega cross RB slash A, then I'm saying, okay, hey, fix the distance between the point A and B and just let the body rotate. Okay, so this is essentially fixing the distance between point A and B to be fixed, which is RB slash A, and then I'm trying to rotate the two with respect to the other. This is just the angular velocity of B with respect to A. Okay, so this is the relative velocity of B with respect to A if we fix the distance between B and A to remain constant. So you see, this is some kind of a velocity that comes due to the rotation of the body. There is another velocity that comes only due to the translation of the bodies, right? So VBA relative is due to translation. Omega cross R B slash A is due to rotation, and so the combination of these is the total relative velocity between B and A, and so we can say that V B slash A is V B A relative omega cross R B slash A. Okay, so this is a very nice thing that we have here. Okay, that did not come out as a straight line, but bear with me for a minute. Almost there. Okay. All right, so in summary, I have the following. Velocity of B. So first of all, position of B is position of A plus the relative position. The second thing is the velocity of B is the velocity of A. Then I'm going to have V B slash A relative, and then omega cross or B slash A. Many times there is a confusion, which omega should I use, omega of body that contains A or the body that contains B. It is always going to be the omega of the body that you are writing as the first term here. Okay, if you're writing the term A here, then it's going to be the angular velocity of the body containing the term A. Okay, now one thing I want to write down here. Okay, so this is this equation. So this equation here, let me say, so if A and B are on the same body, what happens? Then R1 dot is equal to 0, R2 dot is equal to 0, which means that V B slash A relative is equal to 0, which means that if A and B are on the same body, right? For example, if I'm not saying that point B is on a different body, but point B is on the same body as A, then the equation that I have is VB is equal to VA plus omega of R B slash A. If A and B are not on the same body, then I have VB is equal to VA VBA relative, and then this omega of R B slash A. Okay, and then VBA relative is R1 dot E1, R2 dot E2, and then R B slash A is some R1 E1, R2 E2. Okay, likewise the same thing here as well. And so these are the expressions that are of importance to us. So this is if they are on the same body. Okay, if they're on the same body, then you kind of lose out the translational relative velocity, because 2 points on the same body cannot translate with respect to each other. But if they are on a different body, that is, if they're not on the same body, then I have this entire big guy that is coming into the picture, okay, where this relative velocity is defined this way, and this is the position vector. The position vector is the same as the previous case as well. I mean, even for the previous case, I can maybe copy this and then I can paste this here. Okay, so that's the same thing here. So that's true there, and that's true there. Okay, so the most general expression is the expression that I have drawn here. So this is the most general expression. So this is the most general case for velocity analysis. Okay, and so what we will do typically is that we will use the big equation. We will always I guess I don't know what happened here. We will use this big equation here, okay? But then we will say, okay, is A and B on the same body, or are they on different bodies? If they're on the same body, then get rid of this VBA relative. If they're not on the same body, then that becomes a scarier proposition. So I have to include this VBA relative. Okay. Thank you very much for your patience. We're going to build on this, and then we will look at acceleration analysis in our next lecture. Okay. Thank you, and take care. Bye-bye.